Look at the Golden Gate Bridge for a second. Really look at it. Two orange towers, a road slung between them, and that long, graceful curve of cable holding the whole thing up. It's one of the most photographed structures on Earth, and you've probably seen it 1,000 times. So here's a question you've probably never asked. What's actually holding up the middle? Because if you look closely, the answer is nothing. There are no pillars under that center span. No columns rising out of the water. Almost a mile of roadway hanging in open air, suspended over one of the windiest, most earthquake-prone gaps on the entire West Coast. The Golden Gate Strait funnels ocean wind like a wind tunnel. The San Andreas Fault sits a few miles away. By every instinct you have, that bridge should sway, buckle, and come down. And yet it's been standing there, calm as anything, since 1937. So how? How does a mile of road hung from two cables survive wind that tears other bridges apart and earthquakes that flatten buildings? The answer is the exact opposite of what almost everyone assumes. When most people imagine why a bridge that big stays up, they picture strength as stiffness, something rigid, something massive and immovable, like a fortress wall standing firm against everything nature throws at it. Hold still, hold firm, never give an inch. That feels right. It's also completely wrong. The Golden Gate Bridge is not built to hold still. It's built to move. The center of that span is designed to swing nearly 28 feet from side to side. It can rise and dip more than 10 feet, breathing up and down with the heat of the day. Right now, as you picture it standing perfectly still, it almost certainly isn't. It's flexing. It's swaying by inches. The stillness is an illusion. But it bends isn't the whole answer either, because bending, done wrong, is exactly what destroyed another bridge, and very nearly destroyed this one too. To understand why moving saves the Golden Gate, you first have to understand what that road is actually fighting. Start with the problem the engineers were handed. They had to cross more than a mile of deep, fast water, currents ripping through at several knots, a channel that ships absolutely had to pass through. That rules out the simple options immediately. A normal beam bridge needs piers marching across the gap, and sinking foundations into that deep, surging water would have been brutally expensive, and the piers would block the ships anyway. An arch bridge would have to rise to an absurd height to clear the channel. Neither one works here, so the only sane choice was a suspension bridge. Two towers, two enormous cables draped between them, and the entire weight of the roadway hanging from those cables as pure tension, all of it pulled tight and dumped into two gigantic concrete anchorages buried on shore. Each main cable is packed with over 27,000 individual steel wires and can hold around 200 million pounds. That sounds reassuring. It sounds like raw strength is the whole story. It isn't, because holding up a steady, unchanging weight is actually the easy problem. Steel is fantastic at that. The thing that destroys bridges isn't the weight that sits still, it's the load that moves. And here's where the obvious solution turns deadly. If wind is the enemy, the gut-level fix is to make the deck thick, solid, and stiff so the wind can't push it around. Build a wall. Refuse to budge. That is precisely what killed the Tacoma Narrows Bridge in 1940. Its deck was built with tall, solid plate girders running down each side, basically a flat surface for the wind to grab. And grab it did. In winds of only around 40 miles an hour, that solid deck started to catch the air like a sail and twist. The twisting fed on itself, building bigger and bigger, until the whole roadway was rolling and writhing like a ribbon. Then it tore itself apart and dropped into the water. It was caught on film, and that footage rewrote structural engineering forever. Now here's the part that should make the back of your neck prickle. One of the engineers who worked on the Tacoma Narrows Bridge had also worked on the Golden Gate. The same era, the same assumptions, the same blind spot, baked right into the bridge you trust today. And in 1951, the Golden Gate came far closer to that same fate than most people will ever realize. A storm came through with gusts approaching 70 miles an hour. The deck began to flutter. Then it began to twist, so violently that the light poles standing along the center of the span were striking the main cables. Engineers who were there said it nearly destroyed the bridge. This was the Tacoma failure mode beginning to play out in real time on the most famous bridge in the world. So what actually saves a suspension bridge? It's not refusing to move. The real enemy was never simple force. It was resonance and twist. Wind doesn't have to be a hurricane to be lethal. It just has to feed a little energy into a twisting motion over and over in rhythm until that twist grows beyond control. A solid, stubborn deck is the perfect victim because it catches the wind and holds on to that energy instead of letting it pass. The fix isn't more stiffness, it's smarter flexibility. After 1951, engineers added lateral bracing underneath the roadway, a web of steel tying the structure together from below so the deck could still flex and sway, but could no longer roll into that runaway, self-amplifying twist. The bridge was allowed to bend, it just wasn't allowed to wind itself up. It survives by absorbing motion and bleeding the energy away, not by trying to stand against it like a stone. And once you accept that this bridge is supposed to move, a second, sneakier piece of genius shows up. In the 1980s, engineers tore out the original roadway, the heavy concrete deck the bridge was born with, and replaced it with a lighter steel one. And here's the counterintuitive twist. They made the bridge thousands of tons lighter, and in doing so, they made it stronger. The new deck could carry more load per foot than the old one, while putting far less mass up in the air for an earthquake to throw around. Less weight to shake means less force trying to rip the structure apart. Lighter turned out to mean safer. You want proof the bridge does exactly what it was designed to do? In 1987, for its 50th anniversary, they let pedestrians swarm onto the span, packed shoulder to shoulder, the heaviest crowd it had ever held. The center of the bridge visibly flattened. The graceful arch sagged by around 7 feet. People panicked, sure it was failing. It wasn't. The engineers were calm because the bridge was doing precisely what it was built to do. It flexed, it gave, then it sprang back. So step back and look at the whole machine. This isn't a rigid monument standing defiant against nature. It's a tuned, flexible system. The cables stretch. The deck sways side to side and breathes up and down. The bracing kills the dangerous twist. Every part is designed to take a punch by rolling with it. It rides out wind and earthquakes the way a reed rides out a storm, bending low and standing back up instead of snapping like a pane of glass. And this is not a finished story. Right now, today, that bridge is in the middle of a massive, years-long, multi-hundred-million-dollar seismic retrofit. Engineers armoring the bases of the towers and replacing the bracing. Also, it can keep moving safely through the big earthquake everyone knows is coming. The whole philosophy is the same as it was in 1951. Don't make it rigid. Make it move better. It doesn't stand still against the forces. It dances with them. And that's the only reason it's still standing. So the next time you see it, that postcard image, the orange towers, the road hanging in the fog, looking utterly frozen and solid against the sky, remember what's really happening. In that exact moment, it's swaying in the wind by inches. It's stretching in the heat. It's quietly riding the gusts pouring through the strait, exactly the way it was meant to. The thing that looks like the ultimate symbol of permanence is actually a masterpiece of giving way. Its greatest strength was learning how to bend. And now, you'll never quite see it as standing still again.